Hi guys! For a bigger project I want to attach metal tabs to 18650 cells. For this I need a spot welder because welding is the recommended method for lithium ion cells. I found this circuit board here on Aliexpress. This variant seems the most promising to me because it can process metal sheets with a thickness of up to 0.3 millimeters. So I'm going to order it now. If it seems interesting to you too, I will put a link in the video description. 1 week later, the circuit board has arrived. This is what it looks like. The workmanship looks good. One small downside is that the rods here are made of brass and not copper. However, they have a large conductor cross-section, which means that the electrical resistance should be still low. The circuit board does not have a cable or electrodes. I want to use tungsten rods as electrodes for the spot welder. These are actually intended for electric welding, but should be very suitable for spot welding due to the high melting point of tungsten. The rods have a diameter of 3 millimeters. Therefore, I have to sharpen the tips on one side each, so that the current flow is concentrated later. For sharpening, I use my good old Makita hand drill with a corundum grinding tool. Okay, that is really going slowly. You can see that tungsten is also very hard. Here I have a terminal block for larger cable cross-sections. I want to use this to connect the tungsten rod to a supply line. Since I want a flexible supply line, I still need a wire protector. This terminal block does not have one as standard. To make a wire protector, I use this tin plate. The sheet is 0.25 millimeter thick, just right for this purpose. Let's see how wide the wire protector has to be. 6.5 millimeters. Yes, that's right. So I make the wire protector about 6 millimeter wide. Now I can simply cut the sheet metal with high quality scissors. Measure how wide the strip is now. Yes, it's just over 6 millimeters. That's good. The strip has to be a little longer than the terminal block is wide, so that I can bend the ends. The first side looks good. Okay, I'm happy with that. Now I'll do the second part exactly the same way again. So both terminals are ready. Now I can prepare the cables. The length should be enough to work well with. I don't want to make them any longer so that the current for welding remains high. Now I can mount it like this. The rod is already rock solid. Now it's time for the wire. Of course, it's stripped too long now. I will just fold the cable over halfway down. Then the clamp will be filled better. Yes, now I can pull the wire out. It's rock solid now too. What a success! Then I can mount the second clamp in the same way. Wonderful! Another small partial success. This is what the two terminals look like now. This should be ready to work. However, I don't like the fact that there is no strain relief or kink protection. Without it, the wire would surely break quickly. To solve this, I want to cut a suitable thick rubber strip. Then I can tie everything down with cable ties. This is what the electrodes look like now. Maybe I will put some shrink tubing over it. Then it will look a little more professional. But first, I want to measure how high the electrical resistance of an electrode is. With a current of 120 amps, for example, the cable drops to 1.56 volts. That's a bit too much for me, considering that the voltage source only has plus 12 volts and there is even more voltage drop at other points on the current path. So every milliohm counts. I could, of course, shorten the supply cable a bit to reduce the resistance. But then the electrodes are simply too long to be able to work with them sensibly. So I'm going to shorten the electrodes first. The question is, how? Tungsten is super hard and difficult to work with. Sawing is therefore out of the question. Do you have any idea how to shorten the rods? Either way, I'll have to remove the electrodes again first. Did you get an idea? Thanks for the input. No material can really withstand an angle grinder, right? We will see. I want to make the cut about halfway along the rod, so now the electrodes are marked. Now it's time to cut. I have no idea how well the grinding wheel or steel parts will cope with tungsten. Hopefully it will work. It will take a little longer, but it seems to work. This is what the cut ends look like now. The heat created these lovely oxide layers, but since these are not electrically conductive, so I have to remove them again. This is what the result looks like now. This means I can work properly even with the shorter cable. But in order to significantly reduce the voltage drop on the supply cable, I want to install a larger cable cross-section. I found this cable with 7.31 square millimeters in my inventory. That's almost 3 times the size of 2.5 square millimeters. So the cable resistance should also be reduced to about 1/3. Let's see how long the supply cable has to be at least. That should be enough. Now let's see how long I have to strip the end for the contact terminal. This is what the ends look like now. In order to install the new cables, I first have to remove the old ones. The old wire was definitely squeezed well. Now I can install the thicker wire. Hopefully it will fit too. I wonder if the cable is now tight. Yes, it can't be pulled out even with force. Now the electrodes have to be connected to the circuit board. Actually, a screw connection is possible here. The current on the positive side flows from here to here. On the negative side, the current flows from the negative electrode from this connection via the press rod to the drain connection of the individual MOSFETs, to the source connection, and then further via this press rod to this connection. What I don't like, however, are the sections without reinforcements. The copper layer on the circuit board is only 35 micrometers thick or even less. That would again be unnecessary line resistance. And the motto already applies: every milliohm counts. This way I could connect the wire more directly. As the copper cross-section is already considerable at above 7 square millimeters, and copper is a very good heat conductor, it takes a while until the melting temperature of the solder is reached. Now I can try to solder the wire directly. That doesn't work so well. But it would be even better if there was soldering on the right too. So I have to remove the solder mask there. Oh, I have to be careful not to scratch too much, otherwise the copper layer will be gone too. The copper layer is clearly much thinner than 35 micrometers. This is what the soldering point looks like now. Not bad, but it's not ideal on the left yet. I like the soldering point much better now. That should be quite low resistance. Then I can try to make the connection on the other side in the same way. That looks really good. There's only little air between the wire and the rod, so the resistance should be low here too. Wonderful. A fuse in the supply line would of course increase safety, but the welding pulse represents a short circuit. To be on the safe side, I have a pair of side cutters ready. In the event of an error, I could then quickly disconnect the connection to the battery. The battery is fully charged. I would like to measure the pulse current. For this, I use this press rod as a measuring resistor. The pulse has a level of 232 millivolts, and 232 millivolts divided by 0.6 milliohms results in around 387 amps. It is also amazing that the battery of my Vespa Pix can supply so much current for a short time. Let's test whether I can weld the 0.2mm sheets with it. No, even now, hardly anything is happening. Oh man, that can't be true. I need a different battery. Luckily, I was also given 4 pieces of 4S LiPo racing batteries with 1.5 amp-hours on loan. These batteries also have XT60 sockets. I've already numbered the batteries. This will help to identify individual battery packs later on. Now let's measure how high the internal resistance of the individual packs is. The first 3 packs show fairly acceptable values, but number 4 has very high values. That's really very unusual. Let's see how high the total resistance of the individual packs is. 52 milliohms, 41 milliohms, 32 milliohms, and 98 milliohms. 98 milliohms? What the heck? But I'll probably only use batteries number 1 to 3 for now anyway, as I don't have enough XT60 connectors. In order to be able to connect the 3 batteries in parallel to the circuit board, I need a 3-to-1 adapter cable. I use XT60 plugs from AMASS throughout as plugs. I've good experience with them. You can find the link to it in the video description. I use 2.5 square millimeters cables here. Much larger conductor cross sections don't fit into the solder cups of the XT60 plugs. Since I keep the cables as short as possible anyway, the higher conductor resistance shouldn't be so noticeable. The real problem is to connect all the cables together in such a way that the contact resistance is as low as possible. The current carrying capacity also has to be able to withstand 1000 to 1200 amps for a short time without anything getting hot. After some thoughts, I came to the conclusion that a homemade crimp connection with a copper pipe is the most promising. First, I have to saw off a 25 mm long piece of the pipe. I bent the piece of pipe a little flat. This creates an oval cross section. Now I can press the middle in on one side using a round piece of steel. I simply use a drill. Ultimately, this gives me 2 through openings to accommodate cable ends. The cable ends now have to be stripped first, of course. I have now put all the ends in. Now I press the middle further using a thicker drill. The required forces are already at the limit of what I can manage. For the final crimping, I squeeze 3 times across with a pair of nippers. This is still doable with hand strength. The cables are now absolutely firmly crimped. Let's measure how high the contact resistance actually is. I have a supply line to my lab power supply here, which is set to 1 amps constant current. If I let this current flow through the line, I can determine the resistance directly with the multimeter. Oh, there's no voltage drop to be measured, so it is probably less than 1 milliohm. That is better than expected, and I'm very pleased. Now I'm curious. I've checked all 3 batteries for identical voltage, so I can connect all the batteries. Now all that is left is to connect the circuit board. I hope that the voltage regulator on the circuit board can also handle 15.2 volts. Okay, the circuit board is turning on. I would set a pulse duration of 10 milliseconds. That is a good starting value. For the test, I cut 2 new strips of the 0.1mm sheet. Now comes the moment of truth. Will it work this time? Look, the 2 pieces are holding together. That looks good. I will add 2 more welding points. Look, the weld points look good. No holes. You can see some melting. If the connection is solid, it must also pass a tensile test. That is very solid. No chance of tearing the connection apart by hand. Look, it's much harder, and it's not the weld points that are tearing off, but the sheet metal around them. It's obvious that the welding is working quite well. So I consider my project a small success. Now I can also add soldering tabs to battery cells. Stay tuned. If you're not already one of my valued subscribers, you have now the chance to become one. Give me a thumbs up and a compliment in the comments. I'm very happy about that, and the algorithm likes that too. Check out my playlists too. There you will find other interesting videos from me, sorted by topic. In the video description you will find links to the parts I have used. Stay tuned for the bigger project. Have a great time. See you next time. Bye bye.